In this video, we will show how we can estimate the change in a multivariable function using partial derivatives. So I want to do this by looking at an example. Let's let t of x comma y be equal to 8x times square root of y be the temperature in degrees Celsius, where x and y are both greater than or equal to 0. So this function, for example, could describe the temperature at different points on the xy plane. All right, and then what I want to do is estimate the change in temperature from the point 3, 4 to the point 3, 4.1 using the derivative. All right, so in this problem, looking at these 2 points, it seems like y is changing. So there's a change in y. And the change in y is 4.1 minus 4, which is 0.1. And x is not changing. X is 3 for both points. So we're going to assume that x is constant. All right. So seeing that y changed by a little amount, but x did not, x stayed constant, makes me think that we want to get the partial derivative with respect to the variable y. All right, so let's compute this partial with respect to y. So to do that, it's going to be helpful to rewrite my function as 8x times y to the 1/2. All right, so at this point, I want you to take 45 seconds or so, maybe a minute, and see if you can compute this partial derivative for practice. So 4, 3, 2, 1, pause the video. Pause the video just for 45 seconds or so. It should be pretty quick. Just taking this partial derivative. All right, so hopefully you did that. Hopefully you tried this and took this partial derivative. So when we take the partial with respect to y, we treat the x as a constant. So 8x is going to stay there. And then we take the derivative of the y to the 1/2 part. The 1/2 power comes down. And we'll get 1/2 times 8x, y to the subtract 1 from the power, and I get negative 1/2. So this is 4x y to the negative 1/2. Or actually, no, it's better to write that as 4x and then over square root of y. That just looks a little bit cleaner. And in this problem, the function represents something. So this partial derivative has units that I can describe. So this partial derivative of my temperature function with respect to the variable y, the units of it are going to be degrees on top, because those are the units of temperature, over a unit of distance, because that's what y sort of refers to here, a unit of distance. All right, so now I'm going to plug in the point 3, 4, because it wanted us to estimate how much the temperature changes if we move from 3, 4 to the point 3, 4.1. All right, so now I'm going to take this partial derivative, del t, del y, and plug in 3, 4 into it. So if we do that, we'll get 4 times the x coordinate, which is 3, over the square root of the y coordinate, which is 4, square root of 4. So overall, I get 12 divided by 2, which is 6. So 6, and the units are degrees per unit distance. So in other words, what this is saying is, if the y coordinate were to increase by 1, if the unit distance was to go up by 1, we would expect the temperature to increase by 6 degrees. Okay, so how can we use this to estimate the change in temperature between our 2 points that we were given? So I'm going to do this in 2 ways. 2 ways that are very closely related. Okay, so the first is to sort of recognize that this number means that T, temperature, is changing 6 times as fast as Y. So temperature is changing 6 times, let me give myself more room here, as fast as Y. Or in other words, the change in T is approximately equal to 6 times the change in y. And I'm writing approximately equal to, because when I use the derivative to approximate how much my function changes, the derivative just gives me an approximation for the amount of change. It doesn't give me the exact amount of change in general. And that's because when we're taking this partial derivative, what it's sort of giving us is the slope of a certain tangent line. But that tangent line may not lie on the surface perfectly. It might be slightly off, and that's why it's an approximation. All right, so we have change in t is approximately equal to 6 times, and the change in y was 0.1. So we have 0.6, and it's degrees Celsius. Those are the units of temperature here. All right. So let's do this another way. So that was method 1. I want to do this in one other way. So this is method 2. Method 2. So they're really similar. The idea behind this is we found the partial derivative of t with respect to y. In other words, this is an instantaneous rate of change. It's an IROC, instantaneous rate of change. But an instantaneous rate of change can be approximated using an average rate of change. And the formula for average rate of change is we take the change in the outputs, the change in our function, divided by the change in the inputs, the change in y. So this is an average rate of change here. So overall, the formula in general for an average rate of change is you take the change, let me write it like this, my change symbol, I'll say delta, change in output over the change in the input. All right, so we know what the partial derivative is. We know that that's 6 degrees per unit. And on the other side, we have delta t on top. Oops, sorry, this should be an approximately equal to. And on the bottom, the change in y is 0.1 units. So if we isolate for the delta t, this implies that delta t is approximately equal to 6 degrees per unit times 0.1 units. And I'm really writing out all the units here in method 2, so I can more clearly see how the units are going to cancel now. Because I see this units here and the unit on the bottom are going to cancel, and I'll be left with 6 times 0.1 is 0.6, and what I'm left with is degrees. So this is in degrees Celsius. All right, so I got the same answer using our 2 methods. So I mentioned that these 2 methods are essentially equivalent. I'm just thinking about it from different lenses. In method 2, I was using average rate of change to approximate the instantaneous rate of change, the derivative, the partial derivative. In method 1, I was thinking about the partial derivative from a more conceptual viewpoint. The fact that we got this partial derivative was 6 meant that t was changing 6 times as fast as the y. So in terms of our goals for this section, we have finished our last goal. We've talked about how we use partial derivatives to approximate the change in a multivariable function. And we will look at that topic in a lot more detail in section 14.6.